So in part D, now we have a non-uniform disk, which has a mass density modeled by this beta times r function. We need to calculate the rotational inertia of the disk about the axle. So the rotational inertia is the integral of the distance squared along the mass. And we can say that dm here is equal to a small mass multiplied by the area. So this will be the density times a small area, dA. And dA, since we're working in circular in polar coordinates, dA will simply be the 2 pi r times dr of a small little circle. So we can say that the inertia is simply going to be the integral from 0 to r of r squared times the density times dA, substituting dm. Now we can substitute everything else as well. And we can say that dA is 2 pi r times dr. So then this will be, if we integrate it out, we will have 2 pi, which is a constant, times beta, which is also a constant. And then we will have r to the fourth. So this will simply be r to the fourth. So the integral of r to the fourth is r to the 5 over 5. And this goes from 0 to 0.3. Plugging in 0.3, we get that this is 0.012 kilograms times meters squared. Then in part 2, we need to calculate the initial acceleration of the Euclidean system if we cut this rope. So what we know is that the net torque is equal to the moment of inertia times the rotational inertia times the angular acceleration. So you can say that the angular acceleration is the torque divided by I. The torque will simply be provided by this little clay block, which will have a torque of the force, which is m times g times r, and the moment of inertia will be what we have calculated of the disk, and then we need to take into account the moment of inertia of the point as well, and we know for a single point is simply m times r squared. Therefore, this will be the mass of it, so 0.6 times 0.3 squared, which is just the radius, and plugging everything in, we get that this is 26.7 radians per second squared.